What's up, my peeps? This is Coach Jay coming live from my house. We are literally, I got home about 15 minutes ago, ate real quick, talked to the wife a little bit. Here I am with you. Just can't get away from you. Can't get away from GAC, you know what I mean? So we're keeping it real, keeping it rolling, and hope this is helpful for you. I'm going to get started very quickly. I don't want this to be too long because I've already done the podcast on earlier today after school. I think it was about 40 minutes. So we're going to get rolling pretty quickly today, and hopefully this is helpful for you. So we're going to do a couple off the homework here. And if you do have any other questions, throw them out there. A little different. This time I want you to text in the group me any questions you have. I'm going to stay away from the YouTube session for sometimes it takes just a minute to check all that. So if you still post on there, that's fine. Just make sure that you also put in the group me so I can see that and go from there. All right. All right. Voters in a large city are 40% white, 40% black, and 20% Hispanic. Now, notice we want a tree diagram. So we're going to kind of go three different ways here where 0.4 is white. We've got black and Hispanic, right? 0.4 is black, 0.2 is Hispanic. Okay. It then says, our political block. Okay. A candidate anticipates attracting 30% of the white vote, 90% of the black vote, 50% of the Hispanic vote. Suppose we select a voter at random, and then we'll go from there. So from the white population, 30% white. So this is attract. This is not attract, right? So 0.7 would be here. Black would be 0.9 attract. Not attract would be 0.1. Okay. Hispanic would be 0.5. And not attract would be 0.5 as well. Okay. Okay. All right. So once we fill this in, the question is what's the probability? So 0.4 times 0.3 would end up being 0.12. So what we're trying to do is find the probability that if I chose a person at random, what is the probability that they would be white and be attracted by the candidate, and so on and so forth. So we're just doing this. So 0.4 times 0.7 is 0.28. 0.4 times 0.9 is 0.36. I'm just multiplying them. 0.4, remember it's and, right? That's why we're multiplying. 0.4 times 1 would be, maybe 0.04. 0.2 times 0.5 is 0.1. And 0.5 times 0.2 is also 0.1. Okay? So when I add all this mess together, I should get approximately, I'm looking here, 32. Yeah, it looks like we've got it. We've got this should add up to equal 1. But then it says find the probability that this voter votes for the mayoral candidate. So what would they, who would vote for this candidate? Well, the ones that are attracted, right? So we would say 0.12 or the white that are attracted. So probability of the whites attracted, WA, plus the probability of black people who are attracted, plus the probability that Hispanic people would be attracted. So we would just add 0.12 plus 0.36 plus 0.1. Okay, and this is the percentage of people that would be attracted or vote for this candidate. So that'd be 0.58, I believe it is. 0.58 would be that probability that is there. So then we say, given that the chosen voter plans to vote for the candidate, find the probability that the voter is black. So if I am given, this was from today, that the voter will in fact vote for the candidate, that means anyone that would not vote is eliminated because what was given was the fact that they voted for the candidate. So out of the 0.58, which is what we added here, right? The 0.58 was given. This is part A. Part B states that out of the 0.58, what probability were those people that voted would be attracted? Black. And we could put 0.36 of those who were black would be attracted. So that would be 0.36 divided by 0.58 here. Sorry, phone's going crazy here. Kind of click that there. There we go. We're going from there. Hope your night, by the way, while I'm calculating this, hope your night's just fantastic. Hope, you know, if you had any games and whatnot. I know the girls didn't get to pull it out there today in volleyball, but I know that I'm just grateful they competed really hard there. So good job, girls. Good stuff there. So we would say it's a 62% probability that the person would be in black given, really this would be it, given that they voted, so I'll put V for voted, for the candidate. And that's how you could write it, where B would be those who were black and B would be those who voted for the candidate. Just make sure you define your variables, and because that will be very important, especially when the FRQ would be very important there. All right, I'm checking the group me real quick, making sure. Yeah, 93 and 99, I'll do that in a second. Someone also asked this one. This is actually very similar, so I'll set this one up. Let's see here. Yeah, this one's very similar. I think some people just asked about the wording. So there's a laboratory test where the detection of a certain disease gives a positive result 5% of the time for people who do not have the disease. Test gives a negative result 0.3% of the time for people who have the disease. Large-scale studies have shown that the disease occurs in about 2% of the population. So when we do this, we either have a disease or we do not have a disease, right? So if they have the disease, about 2%, so 0.02 and 0.98 are the not disease. Now, if you have a disease, we could either have a positive or negative result, okay? Make sure. Oh, yeah, okay. So no disease, positive, and negative, okay? So it's possible, so it gives a positive result 5% of the time for people who do not have the disease. So if they do not know disease, they still give a positive result 5% of the time, and the negative result 0.95% of the time, or 95% of the time. The test gives a negative result for people who have the disease, so I have the disease, but yet they give a negative result 0.3% of the time, or 0.03%. This would be, move it twice, so this would be 0.003, and then this would be 0.997 up here. So once I kind of set this up, I do the same thing as I just did in the other one by finding the totals by multiplying 0.02 times 0.997, go from here, and so on and so forth. But then it asks, what is the probability that a person selected at random would test positive for the disease? Well, those that would test positive out of the total of 100% would be this, or, and this is where we add, right? Or this value once I've multiplied. The next one says, what's the probability that a person selected at random who tests positive for the disease? So this is what is given, right? Remember, whatever's given goes on the bottom of the fraction, and we put the part of what we're trying to find on the top. So the given would be actually what we found here, because that's the same thing, right? The select at random those who test positive for the disease. Does not have the disease. This would be does not have disease. So we would say that it would be the 0.05 over whatever the given is that they tested positive, in fact, for the disease. Okay? Cool. 95. Let's get it. We're going to be fur today. I'm going to be fur. All right, let's see here. My question is this: what do y'all think about me? Sometimes I feel like I think you maybe just wonder just a little bit about me. Wonder if I'm okay. I just want you to know that I am fine. I am good to go. Never been better. So just a heads up on that. I don't know if you were worried, but just in case. All right, here we go. Let's go to number 99 is a good one. And number 93. I will talk about 93 real quick. Got you out there, Eric. Just a little heads up. Number 93. So think about this. Some TV show begins after their scheduled time when earlier programs run late. According to a network's record, 3% of its shows start late. To find the probability that 3 consecutive shows on this network start on time. Now it's consecutive. Here's my big thing. If one show starts on time, is that dependent to whether the second show starts on time? Is that dependent to what the third show starts on time? My big thing is, and I used to hate it, it's not as bad anymore, but sometimes if one show runs late, the next show runs late, and then it's just a spiral effect, right? Especially if you have sporting events that go into TV shows. So because of that, we would say that we cannot simply multiply 0.97 times 0.97 times 0.97 because these are not independent events. What happens on my first show, that is late, that will impact, or even on time, that will impact the probability of the second show being on time or not. So we would say that this would not be sufficient, and as a result, would not be able to multiply that together because these are dependent events, not independent. What? Yeah, I know I'm not showing that question. I just want to simply talk through that one because I was going to come to number 99, but I think 93 really, I don't think I have to go through that in too much detail, to be honest. Again, remember that when we're referring to a dependent event, we've got to what happens on. Sorry, I was trying to Mike and Ike. Sorry about that. I do love Mike and Ike. What we would say in that situation is the probability would be different. It wouldn't be just 0.97 times 0.97 times 0.97. The one program being on time or not would make it either higher or lower the probability of 0.97, depending on whether that one was late or whether it was on time. Cool? Cool. Hey, Eric, just give me a little shout out, just a little whoop whoop if you got, if you're good, or just tell me fur, and we'll be good too. Okay. All right. Next one, number 9. If this die is thrown in the top, by the way, this is a loaded die. What is given to me is this right here. I think this was one of the top ones missed on the quiz, one similar to this. If this die is thrown and the top face shows an odd number, what is the probability that the die shows a 1? Okay. So if this die is thrown and the top face shows an odd number, that is given, right? We are saying that is true. So we can either have for our odd numbers, those are our odd, right? Boom, boom. All evens are gone like a freight train. So this would be for an odd number, 0.3 plus 0.1 plus 0.1, which would be given. So it's the probability that this would show a number 1 given that the number was odd. So if this is true, well, it is true. I'm sorry. The given part always goes on the bottom. So when I set this up, the given part would be 0.5 probability. Those are what I'm focused on. What is the probability that given that it would be the number 1? Well, the number 1 would be probability is 0.3. So this is the part over the given. So the part is 0.3 over 0.5. And when I do 3 over 5, we get 0.6 or 60%. And that would be E. Cool. Awesome. And that's how we would focus in on it. Cool. I'm looking and seeing any questions here. All right. Do y'all have any other quick questions on that? Just looking on there real fast. I thought I had. There's some good stuff on the podcast that I think you should check out. I don't think I hit any of these. So for literally like just a little bit, because I don't want to go too late. I'm just going to go over how you would approach some of these multiple choice questions. No. You know what I'm going to do? I'm going to help you on one FRQ. You ready for this? All right. What if I said this? All right, here we go. I've got a 5-sided die. 1, 2, 3, 4, 5. Okay. I don't even know how that would work, but just go with me. Dream it up with me. Okay. We have a 5-sided dice. Okay. And that's for you, Lindsay. So let's say that the number 1, 3, and 5 has twice the likelihood. This is a loaded, right? Meaning it's cheat. It's a cheat code. Okay. The 1, 3, and 5 have 2 times the likelihood of being rolled compared to 2 and 4. Okay. So how do I figure that out? How do I figure out the probability in this model for that? Well, if I say it's 2 times, think of this in terms of for every 1, 2, and 4 get, right? If it's twice as likely to land on here, for every 1 time it hits 2 and 4, it will hit 1 2 times. It'll hit 3 2 times. It'll hit 5 2 times. If that is really truly the probability that's there. Okay. So with that being said, we have 1, 2, 3, 4, 5, 6, 7, 8. So we would say that the probability of getting a 1, the total is 8, right? So here's the deal. All of these are going to be over 8 because that's my probability. Now, could I reduce it? The answer is yes, it absolutely could be. But when I think of the total of 8, the probability of getting a 2 would be 1 of 8 because it's loaded. Probability of getting 4 is 1 of 8. Probability of getting 1 is 2 of 8 or 1 of 4. 3 would be 2 and 5 would be 2. And you could reduce these as well. But just understanding that when I say that there's a 5-sided dice or something that's is this much more chance of getting it than these numbers, it's just something to think about as you're approaching this problem here. Okay, let's see if we got. Let's see if we have this one. Good. Okay, so that's our two-way table. There's one I thought that there was one I wanted to hit on. Sorry, I'm talking to myself. My apology. Number 1's a big one. I would look at that one. That one's on my last podcast. Yeah, it's a really good one. No mutually exclusive and independence and the formulas that are for each. So if you look at, for instance, this, if I say something's mutually exclusive compared to independent, you need to know what the differences are. So remember, this is or we traditionally add, right? And this is and we traditionally multiply. Independent states that the probability of A is equivalent to the probability of A given that B occurred, and is equal to the probability of A given that not B has occurred. But if I can show that these two are not equal, then we would say that it's not independent. So if I say something is independent, we would say that probability of A is equal to the probability of B. I'm sorry, back up. That's not right. Okay. So if this is not true, let me back up. If these are not true, then it's dependent. It's not independent. But if I say what's the probability of A and B, this is what I wanted to say. Then if it's independent right here, we would say that it's the probability of A multiplied by probability of B. So these two would equal the intersection. Remember, what is intersection? It's where both occur in my Venn diagram right here. But if it's mutually exclusive, by the way, the intersection, that's not independence. If this right in the middle is equal to P of A times P of B, then that's independence. But mutually exclusive means that when I do P of A plus P of B, that equals P of A or B. And what does that mean? Well, remember, the probability of A and B, or the intersection here, is equal to 0 when something's mutually exclusive. Think two circles with no intersection, okay? There's no intersection here. So that's something to just remember when we're referring to independence and mutually exclusive. Cool. Perfect. Hey, I don't see any other questions here. I'm trying to see if I see any other major ones before I get it rolling. I think we're good. Oh, yes. Oh, hold up. Let me get this here. Perfect. Hey, I hope that was helpful. This is just a quick Q&A. And if you've got questions tomorrow, I'm going to hopefully go through some more stuff with you. And both podcasts are going to be good. I would check both out if you're looking at this maybe a day later because you have the test on Thursday. Yeah, I would just maybe if you have questions, come on in for some extra help and we'll get it done. Other than that, peeps, have a great week, rest of your week, and enjoy block day. We will have the first about 30 to 40 minutes to prepare. We'll go over some multiple choice questions and we'll go over some of those things and we'll rock and roll. Other than that, be blessed and love you all.